Okay, chapter 13 moves us right along to correlation and linear regression. To define our learning objectives here is first we will explain the purpose of correlation analysis. Secondly, we will calculate a correlation coefficient to test and interpret the relationship between two variables. Third, apply regression analysis to estimate the linear relationship between two variables. 4, evaluate the significance of the slope of the regression equation. And finally, number 5, evaluate a regression equation's ability to predict using the standard estimate of the error and the coefficients of determination. All right, so correlation analysis. First, let's look at what it is, or how do we define a linear relationship. You know, imagine that we put our X and Y axis up here, and let's just start putting dots. And remember, we're going in this direction, in this direction. And throw something here, make sure my dots are appearing. Okay. And let's say that we are time spent studying. We want to test at the time spent studying is correlated or has a linear relationship to the final grade. Okay, so would we say that this has a linear relationship?
Yes.
Yes. If you saw this graph, what we just see here is a scatter plot. Okay, and again, courtesy, other than my drawing, use Excel's function or Minitab's function to go in and populate. How would you interpret this graph?
That the time studying does correlate to the final grade because it's going up.
Correct. We kind of see a general trend here that as I move further out on my x-axis, I also am rising up on the y-axis. So I see that there seems to be some type of positive relationship between these two. Okay, so we might say these two are correlated. Now, how would I want to test correlation? And even though I threw these two little items out here,
Yeah.
you know, again, we would define these as outliers. And you know, the fact that there's only one of them out there, two of them out there, you know, let it not disrupt our trend here.
Doesn't. Yeah.
So in order to test, we want to look at the correlation coefficient. And we are going to define that as R. It's going to show the relationship and the strength of the linear relationship between two variables. Now these two variables are ratio to scale. You know, we would define them, but it's going to show the strength and the direction of this relationship. It's going to range from -1 to 1. A value of 0, how will we define it?
Be the middle.
Neutral. So we're going to say that there's little linear relationship. How would I define a value for positive 1?
There'd be a stronger relationship.
Well, we'd say that it's positive.
Okay.
And you're right, as we move closer to 1, we say that it gets stronger. The same thing with a value over here of negative 1. A negative 1 is going to show us that they are negative correlation. And as we move closer toward the -1, we would want to say that there is a negative linear relationship. You know, here we're talking about inverse relationships.
Mm-hmm.
If two things are negatively correlated, what do you expect?
They're not correlated at all.
We expect them to move apart. Yeah, they could be correlated. They're just correlated in a negative way.
Okay.
There is still definitely a relationship between the two.
But less of a relationship.
Well, I don't want to say less, depending on how strong.
Okay.
We're just going to say it could be, you know, I could say that there is a strong correlation at -1. It's just negative.
Okay.
So remember, anywhere in the middle, call it moderate. You know,
Okay.
0.5 moderately negative, 0.5 positively correlated. Now, how are we going to compute this correlation coefficient? It's going to say that R is equal to the sum of what?
X minus.
Define those to me.
So it's going to be X is the representation. Like X would be.
And what's X bar?
Is the standard deviation. No, X bar is the mean.
The mean of?
The population. No.
Mean of the population is mu.
Mu, that's right.
It's the sample.
Sample mean.
Mean.
Okay.
All right. And what are we going to divide this by?
The n minus 1.
N minus 1.
Times Sx and Sy. Let's get X and Y on there.
All right, so it's going to use X and Y.
Mm-hmm.
So the standard deviation of X multiplied by the standard deviation of Y. So let's look at an example from the book. All right, Copier Sales of America. Are you with me?
Yep.
All right, Copier Sales of America has a large sales force throughout the United States and Canada and wants to determine whether there is a relationship between the number of sales calls made and the number of copiers sold that month. The manager selects a random sample of 15 representatives and determines the number of sales calls each representative made last month and the number of copiers sold. Determine if the number of sales calls and copiers sold are correlated. So let's tweak this a little bit. We're going to call this copiers sold. What do we want to put down here?
The number of sales calls.
So number of sales calls. Okay, and we see some data Let's get back up on the board there. Computer's wanting to update.
Okay.
Okay, so copiers sold and sales calls. And we see that there is a chart. If we look at the data that's charted, we'll call this our Y, and we'll put it on the X. So this is our Y-axis, this is the X-axis. Remember, when I ask what went into our variables here,
Mm-hmm.
okay, so we see that we charted the data, and how would you describe that data in the text?
That is correlated, that the number of sales calls.
We do see that it's correlated,
Mm-hmm.
positive or negative.
Positive.
Positive, because we see a chart.
Mm-hmm.
When we see a graph, we're presented with a graph moving in this direction. Only thing is we have more than, let's see here, how many samples do they have? So they're ranging 0 to 200 and 0 to 80 copiers sold. And they're going to be somewhere, if I call this 40, we'll call this 100. So they're somewhere up in this direction.
Mm-hmm.
Okay, so yes, definitely say that there is. Okay, so let's use our 6-step process. Okay, let's see where I can put this up. Come over here. Hopefully you're going to be able to see more. Under 6-step process. It's not going to show up good on the video. Let's come back over. We're just going to take it along the bottom.
Okay.
So what's the first step?
Establish a null hypothesis.
Establishing the null hypothesis. And what is our null hypothesis? What's it asking us to test?
The correlation between sample reported. What observations can you make about the relationship between the number of sales calls and the number of copiers sold?
Okay, so the null hypothesis, we're asked to test if there's any correlation between these populations. So the null hypothesis is that the correlation coefficient, we're going to say, we're just going to say that the correlation is equal to 0.
Okay.
The population is going to be equal to 0. Therefore, the 0 correlation. Our alternate hypothesis is what we must accept if we reject the null hypothesis would be what?
The same, that it's equal to 0.
It is not equal to 0. So here we want to say that correlation is not 0. Step 2, test the level of significance. Let's put it right here. Still got it. What's it asking us to test that? .05. Step 3.
Where'd you get the 0.05?
Identify the test statistic.
So if it doesn't give it, do we always just assume it's 0.05?
No. It doesn't give, the problem, you're right, the problem does not give where we want that. What method would you use of interpretation? If you were forced to decide, which is common, it's been given to us at this point. But what method would you use to determine what level of significance you wanted to test at?
I would use the F.
No, you're getting ahead of yourself.
Okay.
We've not selected the test, you're getting on to
Oh.
step 3.
All right.
Okay, you're asking, how did I come up with 0.05?
If you use 0.05, that's going to be on both sides of the.
We're not getting into one tail or two tail yet.
Okay.
Why did I choose 0.05? Why might I have selected 0.05?
It's in between 1 and 0.
Let's flip back there in the text and review.